All right, now I'm going to just tell you about something called Tukeys quick test. Um, this is one that you can do without any charts. Okay, you can just do it on the. Originally, this was, Tukey came up with this in 1959, and this was part of. He came up with a lot of these kinds of things that people could just use, on the factory floor, on a farm, where they didn't, there were no there were no electric calculators in those days. Nobody had computers except huge corporations. Your average farmer didn't have a set of statistical tables or even a slide rule, which is what we would have used back then. It's just a quick test that you can do to test for a statistically significant difference if your data has certain characteristics, which I'll take you through. So the little scenario here, this is made up data. You've got a restaurant which is doing click and collect orders, and an issue for them is how long it takes to prepare the order. So they get an order from a customer, an online order, and that triggers some process, which at the end of which is the food packaged up and ready to be collected. And what they're interested in doing is seeing whether they can reduce the time it takes to prepare the food orders. And they've come across some software which supposedly can sort of, sit between the online order and the kitchen, that will tell the kitchen in what order to prepare the components of the order, in order to reduce the total time it takes to get the order ready. I don't actually know if such software exists, but it wouldn't at all surprise me if it does. And if it doesn't, there might be $1 to be made inventing it. Okay, so what we have is a little experiment. So this sort of experiment is called a before-after experiment, or an interrupted time series experiment. And because it's an experiment, you can kind of draw causal conclusions from this. Okay, it's not done in a super scientific way, but it's actually not too bad. So over a 2-week period, they take a random sample of 15 orders, manually collect the data to check the time between when the order was received and the food was ready for collection. Okay, so they got a sample of 15. The population there was, we could say was, well, we're probably really thinking about the future, but the population they actually worked with for collecting the sample was all of the orders for that 2-week period. And then they installed a trial version of the software, and they used that for 2 weeks, and they did the same thing. They took a sample, random sample, of 15, but something went wrong with the data collection, as so often happens, and so they only ended up with 14 data points, not 15. So I put the data there in tidy format. Okay, that's what it looks like in tidy format. As I've said before, most of the time you probably wouldn't use a tidy table in a presentation. You would present it in some other way that's easier for a human to absorb rather than a computer. And so what I've done here is I've put it into a table where you've got the two samples, and they are sorted from the shortest time to the longest time. Each one is sorted. Okay, the fact that they're in a table together doesn't mean there's any relationship between the rows. Okay, they are not, those rows are not observations of a single thing. They're quite separate. But that's a convenient form to put the data in for this thing that's called the quick test. Now, if we do the box plot thing, there's our box plots. You can just look at that and apply the first rule that we looked at and say, yep, 95% confident or better that they're different. But if you don't have the box plots, then you can try using this thing called the quick test. And the quick test is, it's an alternative to the 2-sample t-test that some of you will be familiar with. So the procedure here is there's a series of little checks you've got to do about the data, and if you get a negative answer on one of the checks, then you can't use the test, and then you have to go on plan B, is the t-test or something. or draw the box plots. But in many situations, you just go through this list and you get to the end, and there's a very simple calculation you do, and you've got your answer. So, it's a good one to know. So rather than go through the list here, we're just going to go through the data and apply the test. So I'll explain what that highlighting means in a moment. There's our data again. Here's what we have to do. So the first thing we do is we arrange the samples in two groups. So we've done that in the table. You can see it there, two groups. And we also have to sort them from smallest to largest. Okay. We need to check, are they less than about 30 in size? Yes, that's good. So this works best with smaller samples. There are more complicated ways of doing it that you can use with large samples, but we're not going to worry about those. Okay, we're just going to keep to this. This is sort of a simple, often where I would consider using this, I don't use it because I can just do this on a computer anyway, but where I would consider using it is if I wanted to just plan a test of something, do a little experiment, wasn't intending to get a huge sample size, just somewhere between maybe 10 and 30 for each group. This is one that I would use, okay, or could use. All right, so samples are less than about 30. The second thing is they need to be roughly the same size. So you don't want the smaller one to be less than about 75% of the larger one. Okay, so they are nearly the same size. That's not an issue, so we're good to go on number 3. Sort them from smallest to largest. We've done that. Now this next test, number 5, is pretty crucial. Does one group contain the smallest value over all the data, and the other group contain the largest value overall? And the answer is yes. So if you look at the data, the baseline control group, that has its largest value is 32, and that is bigger than anything in the intervention group, the group that used the software. And the intervention group, the software group, its smallest value is 8, and that is smaller than anything that is in the control group here. Okay, that the smallest value in the control group is 17. So we passed that requirement, number 5. Okay. Now, just for the purpose of the notation, we'll call the group with the smallest value overall, we'll call that A, so that's our software group, and the other group we'll call B. B is the control group. Now what we want to do here, firstly, is we want to count the number of values in A in the group with the smallest value that are less than the smallest value in B. So that's easier if we just look at the data. This is group A here, the intervention group, and the smallest value in group B is 17. So we've got 1, 2, 3, 4, 5, 6 values in this group that are smaller than anything in this group. So we make a note of that 6, we're going to call that C subscript A. And then in the next step, we want to look at everything in B that is larger than anything in A. So the biggest number in A is 29, and we've got two numbers here, 31 and 32, that are bigger than 29. So we've got CA is 6 and CB is 2, sorry. And so that's 5 and 6 taken care of here. So we just add them up. Okay, sorry, 6 and 7 rather, taken care of. So we add them up. So we've got 6 and 2, add that together, we get 8. Okay, so what the rule says is if the sum of those is greater than or equal to 7, then we can be 95% confident the population from which A is drawn is different to the population from which B is drawn. In our case, we've got 8, so 8's greater than or equal to 7. Okay, so what we conclude is that the preparation time here in group B it's greater than the preparation time on average in group A, and that's a statistically significant difference, that we're 95% confident about that difference. Okay, now we've talked about the populations here. This is my statement of it. We're 95% confident that preparation times will be shorter when using the software than when not using the software, and we can do this little thing that people do in scientific journal articles. We can say what test we use and give some numbers, okay, and a citation. So Tukey quick test T equals 8, N equals 15 and 14, that's the two sample sizes, and then we give a reference. And that's the reference there. It's a 1959 paper by John Tukey. So if you wanted to, if this test worked, okay, if the numbers were right, and if you wanted to look sort of more scientific about how you were doing this, you could write something like that. And what that will probably do, if you're doing this in an assignment, it'll probably send your lecturer looking for Tukey 1959 because they've probably never heard of it. Unless they're a statistician. If they're a statistician, they'll know about it. But if they're not, they've probably never heard of it. And then they will be confronted with a paper that has a whole lot of mathematics in it, proving that this is a perfectly good statistical test for the difference between two populations. Okay, so it's one that it's there may be situations in the field where you might want to use this. It's one that you may want to use yourself if you haven't studied statistics, but you want to produce a claim about a difference in two populations, and the data happens to be, the samples happen to fit all these requirements. And as I say, they often do. Where it falls over most commonly is number 5. Okay, so it's number. People often have samples that are less than about 30, and that 30 number is not very strict. If it's 40 or 50, that's fine. It's number 5 that is potentially a problem. And look, what happens if you hit number 5? My advice is, well, that's when you need to think about doing something else. You can try doing the box plots. Do the box plots with the notches. That may give you an answer. If that doesn't give you an answer, that's when you need to start looking at some parametric statistics. Or the notes here, I've got quite a bit of blurb about t-tests and things. You can read that if you're interested in it. So my next step, if I were using that and I didn't get a result, the next thing I'd look at is this data suitable for a t-test? And I've actually written out there a version of the suitability requirements for the t-test. It's mainly actually to give those of you that don't know how a t-test works, to give some idea of the kind of things that you have to check, so that you understand that one reason for knowing some of these non-parametric tests that I'm showing you is that there are going to be situations where they actually work better. The other way of doing all of this is a technique called bootstrapping, which I've mentioned a little bit earlier. I'm not going to explain what that is, but it's a sort of a Swiss Army knife of statistical tests. So I could use that to find a 95% confidence interval for the difference between the medians. And it's not, once you know how to do it, it's not terribly hard to do it to do. So I haven't done it in this case, and I did give you box plots, didn't I? See, when you look at the box plots, there is a difference in the variances. So this one has more variance than this one, and there's one little outlier. It's not much of an outlier there. So I actually did. Again, this is for the benefit of people who are used to t-tests. I actually did the t-test. I tested it with and without the outlier. There was still a statistically significant difference. One thing the t-test does is it gives you a confidence interval. Okay, so the t-test tells us that the 95% confidence interval for the difference is between 2 and 10 minutes, and the quick test won't give you a confidence interval, at least not easily. Okay, so there's a bit of technical stuff on that page that for the purpose of the test that's coming up in week 9, you don't need to worry about it. It's really there as kind of background for you in the future. My advice to people is, if you at some point if you've already studied statistics and you haven't learned how to do bootstrapping, I really suggest you learn how to do it. Okay, it's a really handy thing. You can sort of do it in Excel, but it's quite clunky. You end up with these huge tables that are thousands of rows long and whatever. So it's better to learn to do it in some proper statistical software. If you haven't studied statistics, and many people who have studied statistics are sort of terrified of studying it, I'm not suggesting you rush into it, but I'm just sort of giving you things to think about here that might suggest to you the circumstances under which it would be worth your while to learn some. It doesn't mean you need to do a statistics course as part of your degree. There are many quite good online courses you can do. Coursera and edX, for example, have many courses, and for those students in China, there are quite a number of universities now in China that have sort of Chinese analogues of edX and Coursera that they're really good. So if you want to learn some of this stuff for the future, it's certainly worth knowing. But in many cases, the best time to learn it is when you think you might actually be going to need to use it, because it's the sort of thing that if you don't use it, you forget it.
Can you please explain bootstrapping again?
Okay, I don't want to go down the rabbit hole here, but basically the way it works, okay, you've got your two samples. Well, it's easy to explain with one sample, okay? So let's just say we're looking for a confidence interval of the median price of avocados, okay? And we've got a sample of prices. So what we do in the software is we take 10,000. Let's say our sample is of 100 avocado prices. So what we would do is we would take 10,000 or 100,000 samples of the sample, but we'd take the sample so that every time we took an avocado price out, we put it back in and then we sampled again. So we end up with a huge long pile of samples. And then we calculate the medians for all those samples. Okay, so we've got 100,000 medians of random samples of the sample. Okay, and then we sort them from the smallest median to the largest median, and then we take the middle 95% of those. We find the middle 95%, the point at which we have only 2.5% below and only 2.5% above, and that's our confidence interval. That's probably the simplest way of explaining it. I mean, there are lots of bells and whistles you can add to that, but that's essentially what you do. So it's in some ways, with a little bit of, a number of you in the class of studying computer science or computing, it's pretty simple to write a computer program to do bootstrapping if you want to do roll your own. But any respectable statistical software will come with a bootstrapping facility built into it. You just need to learn how to use it.
So are those box plots considered to be bootstrapping per se?
No. So bootstrapping is you can't do it without doing something on a computer, those box plots there, for example, they're just based on the data that's in that table.
I know that, but I was just thinking, is it just another name? But it's not. It's something you've got to do with lots and lots of data.
You don't need lots and lots of data, but what you do is you take your data. You can do it with quite small data sets. But what you do is, so if I've got my 100 avocado prices, what I do is I create another 100,000 samples. But my samples are all made of numbers randomly selected from my original sample.
Okay, so is there any point in doing it?
It's a very good point in doing it, because it gives you a confidence interval for the difference in the medians, and you can use it for, the reason it's attractive is you can use it for getting confidence intervals for lots of statistics for which there is no formula for a confidence interval. So if I want a confidence interval for the interquartile range, for example, I can get that by bootstrapping. If I want a confidence interval for the standard deviation, I can get it by bootstrapping. So it's actually very powerful, very useful technique. It should actually be used more often than it is. These days you will come across it in articles, even in psychology and so on. But it's a very, very handy technique once you know how to do it. It's not terribly hard to do. but it's also not something that's taught in most introductory statistics courses. I mean, if you're teaching an introductory statistics course and you're getting students to use statistical software, my view is you should teach them to bootstrap. It would save a lot of headaches, because it gets, you can bootstrap a t-test, and it actually takes away some of these limitations about outliers and distributions and things like that. But this is kind of getting quite a bit beyond the scope of what we're doing here. If I were teaching introductory statistics, I'd be getting you to bootstrap a lot. I would actually use it as a teaching tool, but that's that's a whole different thing. So, but good question. So